So from last time, we saw that every unitary representation of a compact group can be decomposed as a direct sum of a bunch of finite dimensional representations. So one of the representation of a group is the left regular one. We can always represent our group on the bounded linear operator on the L2 of G. And apparently, if your G is big, when it's infinite, this L2 of G is infinite dimensional. So your lambda is not a finite dimensional representation, so it will be decomposed as a bunch of finite dimensional ones. So one big question I want to ask is how can we decompose this left regular representation into finite dimensional irreducible representations? Okay, so that's kind of the big question we're working towards. And this is going to be the main goal of this lecture and also the next. Basically, we're moving towards this big theorem called the Peter-Weyl theorem. Basically, we're going to give a decomposition of the L2 of G into a bunch of invariant subspace for the lambdas. And then we'll show that this lambda is basically a direct sum of a bunch of irreducible representations with certain multiplicity. So that's the goal of the next two lectures. So let's start by giving out some technical thing called the matrix element or matrix coefficient. So here's the definition. So let's let pi from G to bounded linear operator on some h pi. This is a irreducible representation. So here, everything here, G has to be compact. So the h pi, because this is irreducible, h pi is going to be finite dimensional. So let's let d pi to be the dimension of this h pi. We know that's finite from last time. All right, so a matrix unit or a matrix coefficient, or I think the Follin call it a matrix element, is the following function. So a matrix coefficient, or Follin's book they call a matrix element, is essentially a map. Let's call it a phi. Let's use pi to denote. I have a pi here. And then I basically give you two vectors, u and v, from the h pi. So it basically maps an element x in G to pi x inner product with, apply to u and then inner product with v. Okay, so this is a map from G to the complex number. Okay, so this is a function on the group. Okay, a complex value function. So here, of course, the u and v, they're from h pi, this finite dimensional space. And one thing you notice is that because your pi is a continuous map, is continuous from G to the weak operator topology, so this phi uv is certainly a continuous function. Okay, so we have each of these phi uv or pi, each of these matrix coefficient, they're continuous functions. Okay, so they're continuous function of G, and because their G is compact, being a continuous function means it's in basically all of the LPs, so that's quite nice. All right, and one particular kind of matrix unit is the following. So if you think about this h pi being a finite dimensional space, so suppose we fix some orthonormal basis, let's say E1 up to E dimensions d pi, so E1 to E d pi, be an orthonormal basis for your finite dimensional space h pi. I can let the following, so I will prefer using notation pi ij of an x is essentially equals to, this phi of ej with ei. So in other words, this is essentially pi of x. You apply the ej, and then you inner product with ei. Okay. So why this function is important is because you can treat, because once you fix an orthonormal basis, you can fix every operator on your h pi into an n by n matrix or d pi by d pi matrix. So here the pi of x, you can think about it as this d pi by d pi matrix where the ij entry is the pi ij of x. Okay, so this is the ith and this is the jth. Okay, so you can think about why this is essentially when you apply ej, you multiply a vector with 1 on the j coordinate, and then you inner product with the thing on with 1 on the ith coordinate, and this inner product basically returns the ij entry of this n by n matrix or d pi by d pi matrix. So this is the picture of these pi ij. So they're kind of the basic matrix coefficients. So if I let the following, so if let e pi to be the span of all these matrix coefficients, so let's say a span of pi uv, okay, so here uv is inside h pi. And of course, you can just convince yourself because of linearity of this inner product, each of these matrix coefficient is basically a span of these pi ij. So once you fix a basis, this is also the span of these pi ij. Okay, so one less than equal to ij less than equal to d pi. Okay, so this epsilon, this e pi, this is going to be a space sitting inside. You can think about it sitting inside C of G, but you can also think about sitting inside all the LP of G, say L1 or L2 of G. And this is going to be a finite dimensional space because you have a finite span. Okay, so here the dimension of your e pi that's going to be less than equal to d pi squared because you have these pi ij is going to span your entire space. All right. Okay, so there are some space inside the C of G, and we can treat it in the L2 of G. So let's do the following proposition. So I want to show that, first of all, if I have two unitarily equivalent representation, let's say pi is unitarily equivalent to pi prime, then the space, this e pi, they're going to give you the same thing, okay? So e pi and e pi prime, they're basically the same functions on G. And I want to also say that each of these e pi is invariant under these lambda, okay, under the left regular representations, and also the right regular as well, okay. Should say also right translation, okay, right translation, okay. So it's both left and right invariant. And finally, if you think about this e pi as a subset inside the L1 of G, L1 of G is an algebra, so you can talk about its ideal, okay? So this is, in fact, a two-sided ideal, okay? So it's a two-sided ideal inside the L1. So by two-sided ideal basically means if you multiply, you convolute anything on the left or on the right, you end up with something in e pi as well, okay? So the proof of these are quite simple. So first of all, if you have your pi prime is equals to some unitary multiplied by pi times the J inverse, then what you have is that whenever you want to multiply this pi x uv, okay, that's essentially just equals to the pi prime of x of some J of u prime, sorry, not u prime, the same u, okay, and then you have the J of v, okay. And so this Ju and Jv, they basically can be any vector inside the H of pi prime. So we have the phi of pi of, if you test it on this UV vector, it's the same as you test this pi prime on the J of u and J of v. Okay, so clearly they will give you the same space, E pi and E pi prime. And why is invariant under this left or right translation? Let's just show the left translation. The right should be quite similar. So if I consider what happens if you want to say pi uv of some x inverse of y, if you left translate it by x, okay, so what you do is that you use the pi evaluate at x inverse y, evaluate on this uv vector, and pi being a unitary representation, so this is just the pi x star, and then you have a pi yu, and then you have a v, but you can move the pi x to the other side. You pretend this is the pi y evaluate on u, and then inner product with the pi x on v. So this is essentially just you evaluate on u and the pi x v, this vector. Okay, so they are the same, so evaluate y. Okay, so if you left translate, you end up with something still a matrix coefficient. Okay, so it's invariant under left translation. You can do the same for the right and just leave it as an exercise. And finally, if you want to show it's a two-sided ideal in the L1 space, so if I convolute with any f on the left, so let's say f convolute with the uv pi of y, so what it does is, let's just write out the definition. So this is the integral of the f of x. I have phi of uv pi of the x inverse y dx, okay, so that's the definition of convolution. And let's just write out by definition. So this is the f of x. I have the pi of the x inverse y test on U in the product with V dx, okay? So what I can do is I can, well, first of all, use the pi x inverse is basically pi x star, and I moved it to the other side, like when I show the left invariance. And you can basically move the f of x to the other side, so you can treat it as some constant. So you fix, what you end up with is you fix the pi of y and then you apply it to u. And then you have the fx, we need a bar here because it's on the second coordinate, it's conjugate linear. And you have a pi x times v, okay, dx. And all of these, because the inner product is a linear function, you can basically move the integral to the right, okay? So this pi y u doesn't really depend on the integral. And you integrate the fx bar, pi x v, okay? But in any case, this is going to be a fixed vector inside your space, okay? So this is in h pi, your f is in L1. Pi of x v is going to be same length as v, so this right-hand side is clearly defining a vector. Okay, so this is going to be some vector in h pi, so let's call it maybe, let's call it v prime. Okay, so this is essentially just phi of pi u is v prime. Okay, so if you convolute something on the left, you end up with another of these matrix element. Okay, so it's closed by convolution on the left, and on the right is essentially the same thing. Okay, so we can do something similar.